All right, so questions were about the volumes with known cross sections. So the first thing we got to know is, like, we got this function y equals f of x, and say we have another function y equals g of x, and the regions goes from A to B. So let's say there's this region here, we'll call it R, and we have these cross sections jumping off the page at us. So I'm going to just draw one of them. So let's just look at squares first of all. So if we take this purple slice, just a random slice somewhere in the middle, and it has a square cross section jumping off the page. So imagine this purple square is coming off the page up at you, perpendicular off the page. Right? That's going to be kind of what we're talking about. And the way that we find the volume of this region with square cross sections is if we take that cross section and give it a little thickness. Now it has a volume. And then if I stack those small little thin slices, we'll call them, with the square cross sections, if we stack them left to right and we add up all those little volumes, we then get the volume of this shape. And so the thickness is going to be dx, which means the more of these things that we insert, if they're like little books on a bookshelf, right? You can kind of picture that. We have more and more books on the bookshelf, the books get thinner and thinner and thinner. So dx eventually becomes 0 when there's infinitely many of these. So that's the magic part there. The integral then adds them all up, starting at A and stacking them to B. So how do we find the volume of a shape like this with a cross section? Well, it's really about this area here, the area of that purple base. If I were to pluck this square off and lay it down, that thin dx, right? We're talking about finding this area here, the area of the base. If I find that area, it's always going to be area times dx. That'll give you the volume of one of these, and then we can add them up from A to B. All right, and this is the general formula for any cross section. Finding the volume, I should say, with any cross section. So it all comes down to finding the area of that square. And to start, what's going to happen is we need to know whether, even if it's a square or semicircle, whatever it is, we need to know the length of this dimension, this side of the square or semicircle or whatever we have. And that length is going to change. The way we find it is if we think of like the blue length, I'm writing it next to it, but it should be right on top of it. That length is the y value f of x. Then if I think of like this green length, that is the y value from the axis up to g of x. So the purple length will always be the f minus the g. I'm going to take out the of x's for now, but they are functions of x. That's why we multiply by dx. That length will always be f minus g. So let's look at the formula for squares. So if we do indeed make a square out of this, and I pluck it off the page and lay it flat, this is f minus g, as we have seen. And since it's a square, the height of this thing is also f minus g. So the area of that base is f minus g quantity squared. When I multiply by dx, that gives it that little width, which gives me the volume of that thin book. And then when I add them all up from A to B, that will give me the volume of that region. So let's take a look here in this guy. So let's make these square cross sections. So you can see we have this region here and the area between it. Now, I can make the books a little fatter right now. We'll do less squares. As you can see, this one has cross sections that are squares. So when the space between the two curves gets larger, the square gets larger. And we're just working on finding the area of one of those squares, then multiplying by that thickness to find one of these wedges or slices or whatever you want to call them, and then the integral adds them all up. Then, of course, what we do is, as we add more and more of them, that width, that dx, goes to 0. And when it finally gets to 0, right, we'll have the shape, the volume of this shape exactly. Oh, it's starting to turn how I don't want it to turn. I want to try to get back to, that's good enough, okay? And you can see the volume of this thing will change. I'm going to leave it like this so you can kind of see the square cross sections. How about if I make them right isosceles triangles? Right, you can see the volume change, the shape changes, and the volume's a little different based on the cross section I choose. What if I choose semicircular? Right, then I have these semicircles. But any way you do it, the volume is going to be the same formula. You got to find the area of the base. In this case, the area of half a circle, then times dx, then integrate and add them up. This one, if I want to find the volume of the shape, I find the area of that triangle, then I multiply it by dx to get the volume of one of them. Then I use the integral to add them all up. So that's what's going on here. Whoops. And this is how you do volume of cross sections, because they may ask you a conceptual question about this, and you kind of have to know how it's built. So that is how it works. So for this square one, this would represent the area right here of the square. So you can see it fits our formula, right? The area of the square for a square base, A would be F minus G squared. What we start to remember is the coefficient that we drag out front, you know? So in this case, it's 1, so we don't really show it. All right, now let's look at something different, not a square. Let's look at maybe a half a circle, just to make it way different. So in this case, now the things coming up off the page are semicircles. So if I pluck that semicircle off the page, I need to find the area of that half circle. Well, I need the radius. The radius is equal to 1/2 of F minus G, because F minus G is the diameter. So the area of that thing will be pi times radius squared. All right, so then I can square both of these. Oh, sorry, and we want to do half of this. Pi r squared is the entire circle. Half of it would give me half the circle. So that's the area of the half circle. So now I can square both parts of this because it's multiplication. So if I square the 1/2, and then I square the F minus G. So the 1/2 times the 1/2 squared, 1/2 squared is 1/4 times 1/2. I get 1/8 times pi. I get pi over 8 times F minus G squared. That's the area of the semicircle. So if I multiply it by dx, that gives me the volume of one of those slices, and then I add them up from A to B. This is a constant, so typically we pull it through, and that's the thing I was telling you to focus on. If you notice, both of these formulas are the same, the square and the semicircle, except they have this coefficient on the outside, or this constant on the outside, right? For the squares, it was 1. For semicircles, it's pi over 8. This formula here for semicircles, it's not going to change, so that will always be the pi over 8 for the semicircles. Let's do a right isosceles triangle. That's another one we see. So if I have my slice here, a right isosceles triangle comes up at a right angle and then makes that triangle there. So I'm going to pluck it out and pull it out on the side. F minus G is that along the base. If it's isosceles and right, then that's also F minus G, right? So the area of this triangle is 1/2 times F minus G squared. That's the area of that triangle. Times dx, we give it a little thickness. We integrate from A to B. So for the isosceles right triangle, when we pull that out, it shows up as a 1/2 outside. So for the square, it was a 1. For the isosceles right triangle, it's a 1/2. For the semicircle, it's pi over 8. The same thing is going to be true for an equilateral triangle. There's going to be some coefficient that always works out. I believe it's going to be root 3 over 4. Right? So that one will be for that one. So that's just an explanation of how it goes. The ones I want to talk about last, again, if you want a derivation of this one, I can do it with you in person, or you can come to an extra help session. The ones are rectangles. So if I make a rectangle here, let me erase this. Let's say we do a rectangle. It's like the square one, but now the height, who knows what it is? It could be anything. So if I pluck it off, They have to kind of tell you about it. Sometimes they say it's twice the base, so then you know the height is 2 minus f of g. Sometimes they just say the height is 3. It's always the same. Whatever they say, it's going to be that height, so I'm just going to call it h because they can change it. H times f minus g times dx makes it a volume, and then I add them up from A to B. Now, if h is a function like 2 times the base, then I have to leave it inside the integral. But if they just say the height is 4 and it's a constant, then I can pull it out. Same thing is true of an isosceles triangle. If I have an isosceles triangle, it's not right, it's just a regular isosceles triangle where those are congruent. If I pluck it off and look at its area, it's f minus g times whatever that height is. They have to tell you the height, right? So sometimes they'll say it's twice the base. So this height would be 2 times f minus g, in which case you'd have to do 2 times f minus g times the base, f minus g. And then it's 1/2 because it's the area of a triangle, right? So that's the area of the triangle. It's going to be 1/2 f minus g times whatever that height is. I'll just call it h for now. Multiply it by dx. That makes it a volume for a slice, and then add up all the slices from A to B. If this h is a constant, like if they say the height is always 3, you can pull it out with the 1/2. If this height is a function, usually they'll say something like it's half of the base, so it would be half of f minus g again. Or they might say it's double the base, so they can say it's 2 times f minus g, or whatever they want to say. But that's how you do those.